Hello, everyone, and welcome. So, thanks for joining me today. And if you're watching this recorded later, good day to whenever you are. What day it is, what year it is, whatever. This content is really going to be useful. So, for people who run Cassandra. So today we're going to talk about vector search, but more in line with people who have to run the server. And this is a different take. I did a similar talk at Netflix recently. It was very popular. It was at a local meetup, and I got asked to do more of it. And so I added some stuff to it and have turned this into an online workshop so everyone can take advantage of it. But it's I think vector search is because it's a hot topic, it gets a lot of play, but then it's mostly about like building apps and things like that. For you who probably run data infrastructure or that sort of thing, this might be a useful talk for you. So let's get into it. So what are we going to talk about today? First and foremost, we're going to talk about like what are vectors. We're just going to level set. I think this is something that I've learned is that people know the words vector search, but they're not sure what it means and how it works within a database. It's not a standard database index, so that's really important. Then getting to some of the implementation details of how it works in Cassandra, which will help you as you deploy it and you're thinking about how you use it. And there'll be a lot of details in there that are really important. And then the vector search use cases, and that'll help you as you work with your developers and maybe even yourself if you're doing the developing. But the vector search use cases are important to understand because then you'll understand what's not a good vector search use case. And that's what usually gets you in trouble with a new technology is you use it the wrong way. And then some operational considerations. And this is some things that I put together just after talking to folks that have been starting to running into production. And, I work at DataStax. We run probably more Cassandra than about anybody in our Astra product. And we've been running vector search for over a year now, and there's just a lot we've learned in here. So I'm going to go through that. So let's start out with, just what is vector search? And vector search, like I said, has become very much the hotness because of Gen AI. And it's this new kind of paradigm that I think this glues into things you already know. So for instance, finding data is a thing, and it's always been a thing with databases and data products. And we've started out with just the exact match, and this value is equal to something, and those are your primary key lookups and that sort of thing. You can even do index lookup, and then any DB does this. This is a core feature. The keyword matching is what has evolved over the past 20 or so years. And that's just, we start out with then we get into things like Elasticsearch, Lucene, Solar, where you can do fuzzy matches and look for words inside of documents, that sort of thing. And that's gotten us pretty far. BM25 is really cool. And, that's the best match 25 BM and exact match. And that has done a really good job of getting us to where we are today. Semantic matching is a different thing. And here we go. Here we're into the new world of search. And it's about looking for things that are similar to each other without actually having the keywords. And that's like doing movies and like finding movies with cats. Like, okay, that's what vector search about. So let's dig into what that is. So important first thing to understand are the vectors are created. So you as an operator or you as a developer have to create the vector. The database just simply indexes it for lookup later. And so it's not something that databases are like, we're used to indexes being create index on some field, and then it just makes sure that field is a fast lookup. Different thing. It's actually new data that's created. And so when we take a title and a description, the thing that you'll hear about a lot is embedding models. And embedding models is the algorithm that's used to create that embedding. And the embedding that's created is just this massive array of floats. And you'll see that some of them are rather large. Some of them get really, really big, like more than 1,500 terms inside of it. So but what those numbers, those groups of numbers represent are just simply the what that is based on the model. And so if we were to look at it a little more in depth, like where does this work in, like from the searching standpoint, like I have this thing of like I want to look for movies with cats as a main character, which is a very difficult search to do in keyword or even exact match because you would have to have some sort of metadata or something like that. But models are designed around the idea of pulling out the semantics, like the meaning of something. And whenever the vector is created with all these different terms in there, but what you're finding is that it's in use your imagination here, it creates this thing into vector space, and which means that there's clouds of things that are closer to each other. So for instance, when I say yes, here's books over here on the left, here's this cloud of books that are grouped together, and then here's a cloud of movies on the right. Um, Whenever I say I want movies with cats as main characters, in this cloud of movies, I'm finding things that are cats. And or I do a search and it goes right where that orange dot is. Well, what's close to that orange dot when I say that? And those closest things are what I want to match with. And that's why we call it approximate nearest neighbor, ANN search. It's like what's near this thing I'm looking for. And it's really powerful. It opens up a whole bunch of different use cases now. The one that everybody's talking about right now is RAG. And what RAG does is whenever we ask a question, it creates the embedding. So it's like we take the question, create an embedding from that, and then do an index search on pre-existing embeddings inside of the database and say what's close to these terms. Semantically, here's a question. Semantically, I stored all this stuff. And what will happen in the database is it returns some rows of data, and you could say, I would like to have these as close as possible, meaning this confidence that it gives you is from a 1 to a 0. Well, a 0.89, 0.92, that's pretty close, right? And I've actually played around with this and done some stuff, and I did find cats as main characters for movies, and there's a surprising number of them. I did when I did it at Netflix, I was showing that you could not look at Netflix search and find cats as main characters. That did not exist, and because it looks for keywords, it's a keyword search paradigm. But whenever I do a cat, if you can go do this in ChatGPT right now, and it'll give you results back. And they're actually legitimate. They're not hallucinations. But in RAG, we take all those examples. We say, find me movies with cats as main characters. We get a result set back. We blend it with the prompt. Then we pass it to the large language model. And the large language model takes all that context, blends the real information, the stuff I pull from my database, with the question I asked, and gives you a nice human readable response like, hey, here's some movies. So that's what RAG is. And RAG is powered by this idea of nearest neighbor search. And this is what we're doing. So how is this implemented? And this is how we do it in Cassandra is just, it's a shortcut to just say, let's talk about JVector. JVector is a project. It's a separate project, but it is integrated into Cassandra. It is baked into how Cassandra works, and I'm going to show you how it works. So the 5 hard problems with vector search that were solved with JVector, and there are many. It's like, pick a database. It probably has some sort of vector search built into it at this point. Like SQLite has vector search. Now, what are the capabilities of that vector search is the question. And it's just another index. It's another typing. But why do we have so many databases? I believe there are like 350 or 400 out there in the world. Why do we have the different ones? Because they all have different features along with their other features. So the big features that we were trying to solve, and this is what was being attempted to be solved by bringing JVector and vector search to Cassandra, are these 5. Scaling out, something that Cassandra's done since day one, and it does it really well. It's the undisputed leader of scale. I think this has been the place where we've played pretty well. You look at the largest data workloads in the world, and it's probably running on Cassandra. If you use a cell phone, I don't care where in the world you are, you're using Cassandra. This garbage collection is also something that is a big problem with indexing, especially when you're updating data regularly. And I'm not talking about garbage collection with Java or anything else. I'm talking about garbage collection of indexes. Um, and then use of disk. And this is a challenge at scale. Like I said, those vectors are pretty big. They can be 1,500 terms. And when you're storing that much data on disk, you better have a plan. And that's something that a large database or a scale database should be able to handle pretty well. This composability is also important. Instead of just doing vector search, and there are a lot of databases that just do vector search, and there's some good ones out there too. But we think that it's a feature and it should be hybridized. You should be able to use it as a composable part of your query. And then finally, concurrency. And concurrency is probably one of the hardest problems to solve in a large scale distributed system. Concurrency means how many users can I have using it at the same time? How many processes can we have using it at the same time? And then on all those processes, how can they stop from like destroying each other? Happens all the time. You know, there's noisy neighbors and that sort of thing. Non-blocking. If I, excuse me, if I'm indexing things, let's say I'm inserting a lot of vectors, I don't want the insertion of vectors to block the next read. This is actually something that vector search or vector indexing was really built around batch processing. And doing batch around vector was the way to do it. You load them all up, you run your indexer, then you could do a read. That was great at large scale. And this is when Facebook really started to make it a thing with their face library, FAIS. But now we want transactional workloads on that. And concurrency is the harder part. A lot of purpose-built vector databases do this kind of store, index, and then make available. And there's vector lag. And that vector lag is index lag. And this is something we found with like Pinecone. And excuse me, 'tis the season. This is something we found with Pinecone. Pinecone does this indexing thing. So if you put the data in there and you let it give it a minute, then it'll come back up to speed. But if you're constantly writing to it, it just gets slower and slower because of index lag. And that's something we solved in Cassandra years ago. I want to say 8 or 9 years ago, was storage attached indexing, some index on write, that sort of thing. We learned how to do that. So that was a hard problem that we decided that this is going to be something we're going to own. And Cassandra does it pretty well. So what is it inside? Let's get into the details of how it works. Well, first and foremost, we have a new data type. The new data type is I think we call it vector. What a great idea. And it's funny, if you've ever participated in open source projects, you know that one of the favorite things that people do in a project is they go on a mailing list or in a chat group or something like that, and they endlessly argue about naming things. And this was one that was surprisingly took a while, but we landed on the word vector. Go team. And so we have a type called vector. It has 2 dimensions. There's, first of all, float, and then the number of dimensional embeddings. Like I mentioned, some of these can get rather big. 5 is probably not a dimension you'll ever use. It's probably more like 1,500 or 700 or something like that. But anyway, this is that second number. That number that you put in there is how many you want to store inside of there. You're basically pre-creating your index before your array. Okay, so once you have the vector type installed, then the next thing you're going to do is create an index on top of it. So it's just another field. But what's interesting, and there's just a little word of warning, there's 2 syntaxes, and it's which version. There's create index and create custom index. Based on the version of whatever Cassandra you're working with, if you're using an older version, DSE, Astra, just go look at the docs and see exactly what it'll converge probably by 5.1. We just had a little messy moment with this. So sometimes it's create custom index and sometimes it's create index. Just go look at the docs at what version you're using. In this case, I'm going to use create index. But when you do a create index on a vector type, it like knows what to do. It's not going to just go create a regular database index. It's like, oh, I need to do a vector embedding index. And so it does all of the stuff in that particular code path. But it's simple for you as an operator. Now, as operators, this is our DDL that we have to understand, and I'll get into like what the ramifications are whenever you do this, because there's no free lunch and definitely no free indexes. Um, but then searching at this point is just a matter of using the new syntax. It's the you do a search for a particular thing and you say order by this item vector, and the ANN of is approximate nearest neighbor of. Just a little footnote: ANN versus KNN. If you know these two terms, ANN, approximate nearest neighbor, KNN is K nearest neighbor. Okay, K is just a letter, but KNN search is exact match. And KNN is it's a heavy operation because it has to look at all of the data. It can't do an approximation. More typical with like in a Spark cluster or something like that, where you process all the data. You say, oh no, these are absolutely the ones. So just to know the difference, and then look cool. You'll look cool at parties when you talk about it. You're like, oh, I know the difference between ANN and KNN. But when you do the search, you pass it a embedding of the thing you're looking for. Okay, so in this case, I used a 5-term embedding, but there's going to be a lot more. If you recall back with RAG, it was like you create an embedding of your question using the same model, pass that and say, what's close to this question? Well, that's where this dimension comes in. And then you give it a limit because you're just going to look for like the top 5, top 10, top 20, whatever it is, and then evaluate. And part of the response you get back is, you can get the coefficient back, like how close was it? And when we work with vectors, and I think this is, I'm going to just really be very clear about this. Embedding models are so important, and this is what this illustration is about using the same model. So when you're indexing data, when you're creating new embeddings to store inside of Cassandra and then eventually index, the model you use for that. And when I say model, I'll show you an example of it in a minute. But when I say model, you're looking for an embedding model. OpenAI has them. Hugging Face has a ton of them. Those models are generally, and some of them are multi-purpose. Some will do images and text and things like that, but some are very specific. Like they will take an image and create a text description of it, or they're really good for certain languages, or they're really good for certain types of data. So like there's one that Google invented for time series data, which I thought was pretty cool. But the model is the key. And that's out of scope of this, but just, as someone who's helping others do their work with vector search, thinking about models, and understanding what they mean. Because here's the thing: if you index or you create the model and you index that, the thing you do the vector search on has to be the same model. It has to be apples and apples. You can't be creating one with one model and trying another model, because that vector search will not work. And you'll be very disappointed with the results. But I just want to make sure we all get this. And when I say embeddings, here's an exact example. There's the generate and store of data of the embedding. This is a real example. This is using OpenAI embeddings. It's the ADA 002, and this is just some Python code that I scrapped together, just tossed it together. And so this generate OpenAI embedding takes a text field, and then it will return back a ginormous number. In this case, 1536. But when I do the insert into the database, I first create. You notice that in the code here, I create this coordinate vector, and it takes that text. And then I store that in my insert. So I pass that in as a parameter to my bind. So that's the 1-2 punch that you have to do. There are some cool tricks like in Astra where we actually have we built in some things. We have if you look on the channel here, we have some really cool announcements. We've done a partnership with NVIDIA that lets you create those embeddings on the fly, which is really handy. That's a cloud thing. And that's something that's really, it makes it easier for developers, especially because they don't have to think about it. But that's not something that's just built in at the base part of the database. It's definitely something in the stream that has to happen. So let's get into some JVector stuff. Like, what is it about JVector that is important and you need to know about? Um, so first of all, it is the efficient compression in this. Let me rewind. Vector embeddings are, like I said, an intense amount of data, a lot of data, and you have to have a very clear picture of what you're doing, and it's all numerical data. GPUs love these things because it's parallel processing. The important thing for you to know as an operator is that those indexes have to get pushed into memory eventually, and that becomes a really big limitation. And when you can't shove as much into memory, you're in trouble. And so one of the things that JVector does really well is it uses this thing called product quantization. And product quantization is a PQ. There's also binary quantization. Product quantization is a much more efficient algorithm, and there will be new ones along the way. But what quantization does is it's basically a compression algorithm. So whenever you have data that's stored on disk, you need to make it really compressed into memory, and that's what this is. The SAI integration with JVector is also something to understand. SAI, storage attached indexes, are built into Cassandra 5. They're in Astra, they're in DSE, and this is just a more general purpose indexing tool for creating indexes on any field in your database. But we use the same code path and the same data pipeline as SAI. So all the indexes go through the same path. But because we're utilizing something that already exists, we already have a ton of efficiency built in. And so we do indexes on write, so we don't have an index lag, and we do fast lookups across terabytes of data. So this is a really cool advantage. Another thing that is turning out to be quite amazing is the latest advancements in the Java Development Kit JDK, 21 plus especially. The memory management in that is amazing. And some of the hooks that are built into the JDK for doing SIMD, the single instruction multiple data, are pretty crazy, and they're fast. We started playing around with JDK 17 and then 19 and like 20 and 21, and like, wow, this is really amazing. But it really does work. So how's it going? Well, Forrester, and if you follow any of these things, Forrester is one of the analyst firms that puts out like quadrants and waves and everything else. Well, Forrester did the evaluation of their first evaluation of vector databases, and they put what we're doing with JVector. Well, it was in Astra, but that's what they evaluated was JVector. Put it right at the top, and that beats like Microsoft, that beats Google. I'm sorry, all of the clouds, and that's pretty cool. And shout out to my buddies over at Zills. They did pretty good too. But from a transactional functional database that you can use, Cassandra's it. So let's dig into some use cases. And again, this is to help them, your developers and folks, like pick good use cases, because when you pick the wrong use case, you pay for it later. I'm going to start with the easy one, which is just product recommendations. We've done this with inference before. Predictive analytics has been doing this for a long time, and it's harder on transactional. There's lots of ways to do it in transactional workloads, but with vector search, you can do a really easy, quick, like how to do a product recommender. So personalized recommendations, it's recommending products based on the vectors and things. And we even have some example code out there. Aaron Plotz, who works here at DataStax, he's done some stuff on building product recommendations on top with using Java and Cassandra's vector search. It works really well. And we're seeing a lot of the retailers doing that as well. It's really important, again, to understand the models that you're using in this case? Like what's a model that can tell me that this is something I want and I don't want? Of course, you don't want to put in front of your customers that you things that they absolutely do not need or want. But this is not something you have to dream up. There's so much good stuff out there on this right now. Similarity functions are important and um, kind of fit this use case really well. The the one, this is what it really like semantic text search, document retrieval. This is RAG. And when I ask a question, this is what ChatGPT does all the time. When I ask a question, it takes my question, creates the embedding, does a similarity search somewhere, and says, "Here's your answer." Now, ChatGPT just pulls it directly out of the LLM, as well as blends it with context of things you might have given it. Now they're doing web search and things like that, which blend in like real-time data with the LLM to communicate a better answer. For you and for what you're doing, this is, I mean, for all the production use cases we're seeing at DataStax, this is it. This is chatbots. This is customer service agents. This is like internal knowledge management. All of that works really well here. And the challenges in here are, again, embeddings, creating the right embeddings, but it's the retrieval part. This is where volume gets at. I've talked to users that have like millions and millions of PDFs. First of all, you have a problem if you have millions of PDFs, but they did. And that search is really important for finding like, what do I want inside of there? And there are so many things to think about there. And this is more of a developer topic for sure. For you, as someone who's running the cluster, be prepared. If someone says we have this semantic text search thing, that's going to be a scale use case probably. And there are things that we'll talk to in a minute, like what kind of similarity function, like cosine, you want to use. I'll get to it in a minute. But this is the one you probably are thinking about whenever you do generative AI and a database. The one that probably will be more evident as we go along, and this is like all of the big LM frontier models are just starting to do image pretty well and starting to talk about it. As of the recording, there's talk about Sora finally being released, and image search on ChatGPT is starting to be a thing, and more of this is happening. And it's the multimodal data, but it does turn out to be really good. The joke, if you've seen Silicon Valley about the not a hot dog, that whole thing, that was basically this, right? You take a picture of a food item and then it checks to see if it matches up with what a hot dog should look like and returns yes or no. It's a Boolean at that point. You could build that in 2 minutes right now. But the thing about this is that, again, embedding models really make the difference, and you have to use the right embedding models to do it. So if your users are like, "Oh, vector search sucks, they don't find anything," they're probably using the wrong embedding model. And it's something to consider. It's also going to be a lot of data. What's kind of cool is it's not anything different if you have a million PDFs or a million pictures. If you use a similar embedding model, it's going to be the same amount of data stored on disk, not including the metadata. If you store the image on disk as well, then then you might find it a little more big. But in this case, vectors tend to even things out. So operational considerations, and this is what I think I've been considering more lately is like, how does this impact your running Cassandra cluster? And it's not free there, but what is, right? And I've broken it down into a couple of areas that I think are important. First of all, is getting you smarter about like when your users ask questions. As someone who runs a database professionally, you should be able to answer the question. So let's start out with some indexing options. So when you create, and this is the other syntax, create custom index. When you create an index, with options as part of the syntax, and those what are the options and what do they mean? There's two big buckets of choices. First is source model, and the source model is a shortcut. It's great. If you create an index that's only built for one particular source model, like OpenAI V3 large, say for instance, all the data that you're going to do on that table is one model. Great. This is your shortcut. You create the index using that. That guarantees that everything's going to be just amazing underneath. You don't have to think about it. It's probably the one you should use if you know what model you're going to use. If you don't know, then you have to get a little more generic and use one of the similarity functions. And there are three. There's dot product, cosine, and Euclidean. And yeah, okay, those are new. And I'll go through those. But the similarity function is the alternative to source model. So let's get into what those actually are. First one is dot product. I should say right off the bat, dot product is the fastest lookup. Period. But it has some guardrails that we should talk about. In this case, this is good for recommendations like, hey, this is similar to this and it's directional, not magnitude. And when we talk about vectors, the direction and magnitude, it's really just like what the model creates and what similarity actually means. So product search is really good for like, hey, this thing is over here, this product recommender, this thing's over here. It doesn't mean how much of it is over there. It's like this thing is next to this thing. That's all you need to know. What's important is that you have to use only the same vector for this, the same size. If you have non-normalized vectors, meaning that in some cases there's 700 terms, and in other cases there's 800 terms, dot product just does not work. It assumes that everything is exactly the same number of terms, which isn't that hard. If you're using the same model, you should be fine. But this is built for just magnitude, so that's why it's a lot faster. Cosine is probably the more generic one for sure. It does direction, and whenever you think about directions in this case, like it's going this direction in vector search, it's like semantic searches, like the thing that I'm saying are in this direction. That's really welcome to vector search. But it's the same topic or the same theme. And cosine works really well for that. If the magnitude is important, then this is definitely a skip. And then the next one will be for that. But if you have to do exact, then there's a different way to do this. But so in the case of like, you just do magnitude, then dot product. If you need exact, then use Euclidean. Cosine is just directionality. And like what I said, it's more generic in this case and great for things like, is this topic the same or this theme the same? Euclidean, of course, last one, it's this precision. It's a higher precision, slower, but it's good for like spatial data, like geolocation coordinates or image features. Euclidean is really good for imaging because it does put you really close to where this thing is. And so if you're looking to make sure you found a hot dog, this is the one to use. And this is also really good for a low dimensional data. There are vector embeddings that are tiny, they'll create a very short array. And those are really important. But if you use Euclidean, you're going to be happier with what the product you get out of it. If you have, but on the flip side, if you have really high dimensional, like the 1500 or more, it can be a little too cumbersome. Euclidean is a highly compute intensive algorithm, and you just pay the price for that as it go along. Cosine is probably going to be the better choice in this case. Okay. Now, index sizing, I'm going to rapid fire go through some operational stuff. And I should add, if you have anything in the chat, you have any questions, just throw them out there. But this consideration for index size is important because we're using a different indexing engine. And I don't think anyone here thinks this, like I said, this is not a free lunch. Of course, if you're going to create data and store it, you're going to have more. But the thing about vector dimensions is there is something to consider. That these, like I said, 1500 term array That's a lot of data. And if every single field has, or every single row has it, it's going to add up. And it's just something to keep in mind. The indexes, large data sets and with high cardinality, like dissimilar stuff, is going to not compress as well. And so in that case, just keep an eye on your indexes and just know that that's a thing that you should be watching. The things you can do to help with performance in this case is, when you're working with developers, you're working with people building the product, you know, evaluate the models you're using and ask questions about the model sizing. So when we get into the best practices, is dimensionality reduction is really, I think, a good place to start. You're going to have questions about, like, what are we trying to accomplish, and do you need to use the biggest, gnarliest model out there? Probably not. And can you get away with a lot smaller ones? The progress on embedding models is really fast. Hugging Face is a great place to go if you want to. They have tables that show like which embedding models and how they have a ranking index, which is better for what type of use case, the sizes that they create. But the models are getting better, and because this is such a mainstream topic, and yeah, it's worth your time to go look at the models. Don't just use the default one from OpenAI and call it good. You're going to get something better out of it. And sparse indexing is, only, index only the necessary columns. If you're indexing everything for just indexing, then, that's just more data you're going to have to do. And, the vector data itself, are you going to store, do you need to store the image, or do you want to store a link to an S3 bucket? I think that in hybrid search, storing the text makes sense. That's a pretty easy thing to store. But when we get to like video and images, do you need to store that in the database, or is there a better place to put that? I've worked with lots of companies that, they store links to where the actual media is, which is even faster because it can be cached. For instance, if it's an image, you throw it behind a varnish reverse proxy or something, and get like some caching out of it. So you're not actually having to store data like an image in a database. You just store a link to it. That's the kind of thing that I'm talking about. And then finally, the monitoring. You really want to watch where your indexes are, like their index sizes. You don't want to have a moment where you're not prepared for the amount of indexing that's happening. And again, this is benchmarking. As people who deploy databases, you should understand the whole idea of doing load testing and benchmarking, because this is new, and just understanding your use case. And you know how this goes. Your use case is an absolute snowflake because there's best practices. And the best practice here is try out your data, get the best data model, get the best embedding model. Now go look to see what a reasonable amount of data looks like. How does that affect your system? How does it affect the CPU? Are you using the right CPU for this? In some cases, older CPUs are not the best choice because there's so much floating point operations that are happening. Those are kind of things. And we deal with this all the time at DataStax. Like I said, we run a lot of Cassandra, thousands and thousands of clusters, and almost all of them are running vector search. So we understand it. And, ARM is a really good choice too. I just throw shout out to the ARM team. ARM running these kind of floating point operations is pretty fast. The other thing is, making sure that you TTL your data. This is just a good general purpose thing for Cassandra operators, and it's putting a timestamp or an expiration date on your data. If you have things that are time boxed, like this is not going to be valid in a month, then put a TTL on it, time to live. If you're not sure what that is, just look up in the docs the TTL for Cassandra. You can put an expiration date in seconds, and it's like a free delete, because what happens is once it deletes, the compaction just drops it automatically. It's one of the unsung heroes of how Cassandra works. And I've seen companies literally build terabyte ring buffers with their Cassandra clusters because and it was maintenance free, just runs. But vectors may be the same thing. If there's a time box for that data and it's not valuable after a month, then drop it. automatically. And finally, the data pruning, which is similar to what TTLs do, but just make sure that that you're removing things that you don't think you need or any. I mean, this is all about just good, thoughtful use cases that you have with your data. And the product is probably one that you'll never remove, but just little things to consider. Okay, now that I've got you all excited for running this, where do we go now? So I should explain like the shape of in the Cassandra world, what's happening with Vector. Vector is a fast mover, without a doubt, and the whole code base is just constantly evolving. And just because there's so much research happening right now, and there's so many things happening. So where do you find things, and what are the differences? On the right, first and foremost, Astra, that's our Cassandra as a service. We data stacks, we spent a lot of time working on vector search. We're going to put the latest version of whatever we're working on right there. And that's just, it is Cassandra. It's the Cassandra code base, but it's running on a cloud. But we also keep it moving forward. The things that we do in Astra, we upstream to the Cassandra project for every version, which takes me to kind of the midpoint here, this data stacks branch. So branch fork. It's the version of Cassandra we're working on, that Cassandra is what's in Astra. But it's also has the bits of the things that we're upstreaming to the Cassandra project. So this is where we keep all of our stuff in sync with the Cassandra project. Really critical, because Cassandra is a fast moving project as well. If you go to the Cassandra project and you go look at the GitHub, there's commits in there every day, all day. And so we keep our things moving. We synchronize it with the project. And then when a version comes out, we basically do a big merge commit, and yay team. That's a challenge, let me tell you. So what you'll find is the latest thing in our DataStax Cassandra repo. And then Cassandra 5, which just got released, does have a version of JVector. It has a previous version of JVector. It's functional, but it's just to let you know that is not the current state of the art right now. And it will be when we have the next release, 5.1. We'll do a merge commit and get it back up to, get it synced up again. This is just how it works with the project. But, this is a really cool thing that a lot of the major committers do on the project is we upstream all our changes through a process called the Cassandra enhancement process. And so if you want to see what's coming, you can see what Apple's working on, you can see what Netflix is working on, you can see what Uber's working on. It's all in the CEPs. And all of the things that we're working on at DataStax are there too. And then finally, if you want a supported version, Astra is a great choice, but that's a cloud service. Our DataStax Enterprise and the Hyperconverged Database HDD, which runs in Kubernetes, they also have that latest branch of Cassandra in there. So you have choices, and how you want to run it is up to you. And then if you just want to go check out JVector, I have the GitHub link. Yes, that's right. It's Jonathan Ellis, one of the first committers on the Cassandra project and also co-founder of DataStax. Yep, he's the guy running every day with JVector. It's pretty cool. He really enjoys it, so it's fun to watch. But that's something to pay attention to, because that's the leading edge of what's happening with JVector, and very research oriented. And then the final thing is we are working with the OpenSearch team to bring JVector into OpenSearch for vector search inside of a keyword search machine. So there's going to be some blending going on there. Really cool. JVector has been recognized as one of the fastest indexing engines out there, especially with like in the Java ecosystem. So it's cool to see other projects picking it up. I think that is all I have, and I've gotten you for 45 minutes, which is great. I don't see any questions here. If you have any, of course, just you can put them in the comments in the YouTube. This will be on YouTube in about 2 minutes. You can put them in the comments. I'm on Reddit. If you're in the Cassandra, slash r Cassandra. Um, I'm in that Reddit all the time. If you have questions about running Cassandra vector search and that sort of thing. We also, I'm also on the ASF Slack. If you're there, Stack Overflow, all the places. So please reach out anytime you have questions. And connect with me on LinkedIn if you want. However you want to do it. We're always ready to talk to you about like how you want to run Cassandra. And we have lots of choices, and you can do it yourself, or we can do it for you. Either way. Thank you, everyone, for hanging out with